In this video, I am going to explain why Lagrange Error Bound makes sense. If you don't fully understand this inequality itself, you might want to go check out my part 1 video first. So one way to prove this inequality is to prove the equation first. So the Taylor's remainder theorem that I wrote down towards the end of my last video, the part 1 video. We're not gonna do that proof actually, so we're actually gonna go down another path. As I said, I'm gonna explain why this error bound makes sense. So I am actually going to prove only a special case, which is not a full proof. However, after watching this video, why not attempt to do a full proof on your own? This process is quite time consuming, and for that reason, we're only going to be focusing on the case where n is equal to 2. But again, if you can understand this proof, you can try to prove it for an arbitrary n later on. Also, for our convenience, in this case, we're making 0 to be our center, and we're only going to consider the x values that are greater than 0. The other case is actually quite similar. Lagrange error bound requires us to find an upper bound for the absolute value of the n plus 1th derivative between a and x. Remember that we said our n is 2, which means we are using the second degree Taylor polynomial. And when it comes to the error bound, we need to be looking at the third derivative of f of x. Let's assume that we have already found an upper bound, and let's call it k sub 3. I used m in my last video, but I figured in this case k sub n plus 1 is a better notation. K sub 3 just reminds us that this is an upper bound of the third derivative of f of x, which is a number, so k sub 3 is a constant. So we're going to be working backwards from here, assuming that we have found this upper bound, k sub 3. So looking at our formula, which is on the top right corner of our screen, we just need to prove, in this case, that the error is less than or equal to k sub 3 times x to the third power all over 3 factorial. I am also using a weird notation here for the third derivative of f of x. This is the same as f triple prime of x, but we will also be dealing with f double prime, f prime in this proof as well. That's way too many primes, so that's why we're using this different notation here. Now we're done setting things up so we can start the proof. Absolute values are confusing, so why don't we just rewrite this absolute value inequality? And graphically, our inequalities are telling us that our third derivative of f of x is bounded below by negative k sub 3 and bounded above by k sub 3. And now let's integrate each part of the inequality from 0 to x. After we integrate, the inequalities should still hold. Should make sense. Because if you look at this first integral here, that represents the area of, well, the negative area of this rectangle right here. And the third integral on the right side here represents the area of this rectangle. Finally, the integral in the middle here represents the negative area here, plus this area, minus this area, and plus this area. Instead of using x's here in the integrand, we really should be using t dt instead. It really is better math. So as you can see that I'm changing them. Now we integrate. Negative k sub 3 is a constant, so an antiderivative of negative k sub 3 with respect to t would just be negative k sub 3 times t. We're dealing with definite integral here, so evaluate it from 0 to x. Next, an antiderivative of the third derivative of f of t, which is just the second derivative of f of t. Fascinating. Well, of course, evaluated from 0 to x. Finally, similar to our first integral, this third integral would give us k sub 3 times t evaluated from 0 to x. Now we just need to simplify by plugging in our x's and zeros. So we have negative k sub 3 times x minus negative k sub 3 times 0, which is just a negative k sub 3 times x. Now we have the second derivative of f of x minus the second derivative of f evaluated at 0. And then less than or equal to k sub 3 times x. So we're like a third of the way through here. We have to repeat this similar process 2 more times. So the integral from 0 to x negative k sub 3t dt. Again, we're changing all the x's in the integrand to t's because it's better notation. And for this middle portion, do not forget to use parentheses. Again, better notation. Finally, integral from 0 to x, k sub 3t dt. Evaluate the integrals, so power rule backwards, negative 1/2 k sub 3 t squared. Evaluated from 0 to x. An antiderivative of the second derivative of f of t with respect to t. That sounds like the first derivative of f of t. And you know what? I'm just going to write f prime of t here because it's easier. Then minus. So the second derivative of f evaluated at 0 is a constant. So an antiderivative of that would be itself times t. Brackets, parentheses are once again necessary here from 0 to x. Finally, this third part is again similar to the first part, so 1/2 k sub 3 t squared. From 0 to x. Plug in zeros, plug in x's, simplify. So negative 1/2 k sub 3 times x squared. Next, f prime of x minus f prime of 0. So for the second derivative of f evaluated at 0 times t, once you plug in 0 for t, that term becomes 0. And let's just finish up this line here. So 1/2 k sub 3 x squared. As I said, we're going to repeat this process 2 times, so we still have to integrate 1 more time. Integrating with respect to t, so negative 1/2 times 1/3 k sub 3 t cubed. Here it comes again, an antiderivative of f prime of t with respect to t, so that's just f of t itself. Minus f prime of 0 is a constant, so an antiderivative of that would be f prime of 0 times t. This third term right here, f double prime of 0 is also a constant, so we're dealing with an antiderivative of a constant times t, which is just 1/2 times that constant times t squared. Here we have 1/2 times 3 k sub 3 t cubed from 0 to x. One more time, plug in zeros, plug in x's, simplify. Again, this middle portion a bit tricky, so f of t becomes f of x minus f of 0. F prime of 0 times t becomes f prime of 0 times x minus f prime of 0 times 0, which is pretty much just f prime of 0 times x. Finally, for the term I marked green up there, once you plug in 0 for t, it's gone. So it's just -1/2 times the second derivative of f evaluated at 0 times x squared. And also less than or equal to 1/6 case of 3 times x cubed. We're done integrating now, so now what? Now let's give our attention to this middle portion here. So this is just algebra, so instead of saying f of x minus this, minus that, I'm just going to group the last 3 terms together. So f of x minus parentheses. And inside your parentheses, all the minuses would become pluses. Wow, how nice is that? I wish I could change some of my college course grades from minuses to pluses just by adding parentheses. Alright, now if you pay close attention to the 3 terms that are inside the parentheses, what are they? Have you realized? They are actually the terms of the second degree Taylor polynomial of f of x. Well, that was pretty neat. Our Taylor polynomial is centered at 0, of course, because we made a equals 0 at the beginning. So, aka the second degree Maclaurin series. So now our inequalities just become this. And rewriting them as an absolute value inequality, we have the absolute value of f of x minus p sub 2 of x is less than or equal to 1/6 times k sub 3 x cubed. This is precisely what we're trying to prove here, because this absolute value is equivalent to the size of the error, or the absolute value of the remainder, r sub 2 of x. And that's less than or equal to k sub 3 x cubed over 3 factorial. Are you looking for more challenges? Say, maybe a complete proof? Why don't you try to use an arbitrary n instead of 2? Even better, try using an arbitrary a instead of 0 as the center. I hope this video was helpful. See you next time. Bye-bye!